Welcome back everyone. Today we'll go into a new chapter named CORDIC. Like the FIR filter, CORDIC is an algorithm that is known to be very efficient when implemented in digital circuit. So let's try to implement this algorithm using high-level synthesis. Today's learning objective is to be able to explain the CORDIC method and implement the CORDIC algorithm in C. CORDIC stands for Coordinate Rotation Digital Computer. It was developed back in 1950s for navigational computers on airplanes. Back then, the computational power of processors was very limited, so it was very difficult to compute accurate values of complex functions like trigonometric functions in real time. So CORDIC was developed to provide an efficient method of doing such computation. It replaces the expensive multiplication with additions, subtractions, shifts, and table lookups. So the fundamental goal of CORDIC is to perform a series of rotations in an efficient manner. So let's start with how to perform a rotation. When you have X and Y and you want to rotate by data, you would multiply by a matrix cosine data minus sine data, and cosine data. This matrix is called the rotation matrix, R data. The new coordinates after the rotations is shown here, but you can also see that this equation requires many multiplications. So let's try to get rid of these multiplications in the next slide. Let's first consider rotation by 90 degrees. The rotation matrix is going to be 0, minus 1, 1, and 0. So the new coordinates are going to be x equals x times 0 minus y times 1 equals minus y, and y equals x times 1 plus y times 0, so just x. So at least for 90 degrees, the only thing we need to do is swap the value of the variables and negate the value of y. So no multiplication is needed for rotation by 90 degrees. And if you think about the rotation by negative 90 degrees, you can see that this will become positive and this will become negative. So no multiplication is needed for minus 90 degrees as well. All right. So let's think about other angles in the next slide. We're now going to rotate by 45 degrees. The rotation matrix would look like this, and the computation would be root 2 divided by 2 times x minus root 2 divided by 2 times y, and so on. So unlike the rotation by 90 degrees, rotation by 45 degrees still need multiplication. This isn't an ideal situation because we need these expensive multipliers. So is there any way to make this constant multiplication any simpler? Well, let's consider this rotation matrix. Since this is composed of ones and minus ones, this matrix is very simple to compute, but this matrix and this matrix is different. So let's try to make it the same by scaling the result of this by multiplying root 2 divided by 2. Okay? Let's do another practice. Take a look at this rotation matrix. It is composed of 1 over 2's and minus 1 over 2's. Dividing by 2 is just a shift operation, so this matrix is also very simple to compute. Just make sure to scale it by root 2 at the end. So the point I want to make is that we want to make the constant multiplication to be a power of 2's so that it will become simple shift operation, and scale it by some factor at the end of computation. All right, so let's try to generalize it in the next slide. Consider the rotation matrix R theta equals to cosine theta minus sine theta, and cosine theta. Let's refactor it using the following trigonometric characteristics. Then the rotation matrix can be written in this form. And now what we're going to do is restrict the values of tangent theta I to be power of 2's only. All right, like this. Then the rotation matrix becomes Ki times the matrix 1 minus 2 to the power of minus I, 2 to the power of minus I, and 1, where Ki is 1 over root 1 plus 2 to the power of minus 2 times I. So power of 2's is the shift operation, and the Ki is the scaling factor. Now this matrix is for rotation by theta, but if we want to rotate by minus theta, we just need to switch the sign here to positive and the sign here to negative. So we can generalize it by introducing another symbol, sigma. So sigma is 1 when the theta I is positive, and sigma I is minus 1 if theta I is negative. All right. Now let's look at the scaling factor K. If we perform n rotations, the K becomes the multiplication of this equation, 0 to n minus 1. The reciprocal of K is called the processing gain, or the CORDIC gain. So CORDIC gain is the cumulative scaling factor which you multiply once after performing a series of rotations. Let's look at this table, which shows the first 7 iterations of CORDIC. When tangent theta equals to 2 to the power of 0, this is the case when the angle is 45 degrees, the scaling factor, which you can obtain by inserting 0 into this equation, is 1.414 to 1. Now let's go to the tangent theta equals to 2 to the power of minus 1. This is the case when the angle is 26.565 degrees. So this is the radian, and this is the degrees. Okay, so when then the scaling factor becomes 1.11803, which you can obtain by inserting 1 into this equation. The CORDIC gain is the cumulative scaling factor, so it is 1.41421 times 1.11803, which is 1.58114. And you can repeat this process for I equals to 2 as well, and so on. And after several iterations, the CORDIC gain converges to a constant number, which is shown here. All right, now let's be specific and see how to calculate the values of sine 60 and cosine 60. We first need to determine how many rotations we're going to perform. More rotations mean better accuracy, but more computation time. For now, let's set it to 5 iterations. So we're going to perform 5 rotations and try to get close to degree 60 as much as possible. As the first step, we need to determine if we are going to rotate by a positive angle or by negative angle. We're going to start at degree 0, and degree 60 is at a positive angle compared to degree 0. So we are going in positive direction in the first iteration. Second, we're going to perform the rotation. We just need to insert I equals 0 in the rotation matrix equation we saw in the previous slide. So the rotation matrix would be this. We insert I equals 0 here, here, and here. Remember that we're rotating by 45 degrees in the first iteration because that is the degree when tangent theta equals 1 over 2 to the power of 0, right? So we multiply this rotation matrix to the initial degree of 0. Then the result should give us the value of cosine 45 and the sine 45. So let's do this matrix vector multiplication. So cosine 45, this one, equals to cosine 0 times 1. So cosine 0 times 1 minus sine 0 times plus 1. So this is a sigma. And it is plus 1 because we are going in a positive angle, right? So times 2 to the power of 0, right? Finally, we need to multiply by the scaling factor, this one, which can be computed by inserting 0 into the k equation, right? Okay, so you can compute sine 45 degrees in pretty much the same way. Now, instead of multiplying the scaling factor in every iteration, let's hold it off until the end and multiply the entire CORDIC gain instead. Step 3. Since we decided to run 5 iterations of CORDIC, we're going to run step 1 and step 2 5 times. And when we're done, multiply the reciprocal of the CORDIC gain for 5 iterations. You can look at the table in the previous slide, which tells us the value is inverse of 1.64649, which equals 0.60735. This is the graphical representation of the CORDIC calculation we have just done now. In the first iteration, we go in positive angle, 45 degrees, but it is less than the target 60 degrees. So in the second iteration, we again go in positive angle, and we go 26.565 degrees. Okay, now it is 71.565 degrees, which is over 60 degrees. So in the third iteration, we go in negative angle of minus 14.036 and change the value of sigma to minus 1. After the third iteration, it is now less than 60 degrees. So in the fourth iteration, we go in positive angle to 64.654 degrees. And in the fifth iteration, we are over the target angle. So once again, we go in negative direction. So the computation pattern is the same. We're just adjusting the amount of rotation we're making with the value of tangent theta equals to the power of minus 1, minus 2, minus 3, and so on. And depending on whether the target angle is less than the target angle or more than the target angle, you're adjusting the value of sigma from plus 1 to minus 1. Good so far? Alright, so if you're lost, I suggest you go over the video again. Otherwise, please go on to solve the exercise in the next slide. Let's solve an exercise. Compute cosine 45 degrees plus 26.565 degrees, assuming the values of cosine 45 degrees and sine 45 degrees are 0.70711. Write down the whole solution equation, similar to step 2 in computing 45 degrees, and check if the result of your computation matches the value of cosine 71.565 degrees as expected. So you can pause the video now and proceed when you're done solving the exercise. Let's see the solution. 26.565 degrees is the case when the tangent theta equals to 2 to the power of minus 1. So cosine 45 degrees plus 26.565 degrees is cosine 45 degrees minus sine 45 degrees times 1. Sigma is positive 1 because we're going in positive angle, and multiply by 2 to the power of minus 1. We then need to multiply the scaling factor, 1.11803. You can look it up in the table in the previous slide, or you can compute with this equation if you want. And if you compute this, you can check that it equals to 0.31623, which is the same as the value of cosine 71.565 degrees. Now that we have seen the algorithm description, let's look at the actual C code. This is the baseline code from our textbook. This part of code goes after this part of the code. Take a look at the function argument. Given the input data, we want to produce the sine and the cosine values of data as the output. And let's assume that the number of iterations is 5. Now, unlike the algorithm description where we add from degree 0 and try to reach the target angle, the C implementations start with the target angle and subtract pre-computed degrees each iteration. So at each iteration, we're going to check if we have reached the target angle, and if we have overshot the target, we'll rotate by a negative angle, and if we fell short, we're rotating by a positive angle. Then we perform the rotation by multiplying the value of sigma and the variable factor, which is 2 to the power of minus sine. Right? Now, if you look at the entire code, you might be wondering why we're not multiplying the CORDIC gain at the end. The reason is that we don't want a multiplier that multiplies the CORDIC gain. So what we're going to do is start with the reciprocal of the CORDIC gain. Then as we make 5 rotations, the gain will be automatically adjusted to 1, and the sine and the cosine values will be normalized. Make sense? All right. Now we have our baseline C code. Let's try to make a Vitis HLS project for CORDIC. Please copy the code from our textbook, figures 3.3, to a file named CORDIC.cpp using Vitis HLS GUI or command line script if it's more convenient for you. Make a new project named CORDIC and add CORDIC.cpp file. Set the clock period to 4 nanoseconds, uncertainty to 1.08 nanoseconds, and keep the default part selection of the AWS F1 FPGA. For the baseline, you can set all types to float. Then we need to make a test bench. First, generate multiple data values from minus pi over 2 to plus pi over 2. Next, compare sine and cosine values computed from the CORDIC kernel, these ones, and the values obtained from the maths.h. The library name is simply COS and SIN. Then you can compare these two values and measure error. There are several ways to define error, which we'll see in the next slide. The simplest way to define error is to measure the maximum absolute value between the computed value and the reference value. But the more commonly used metric is root mean square error, which is computed by summing up the square of the error divided by the number of samples and taking a square root. Another very commonly used metric is signal to quantization noise ratio. It is 10 times log base 10 summation of the signal divided by the error squared. The choice of these error metrics will depend on the specification of the application. If we were to measure the error of the baseline implementation with these metrics, you'll obtain these numbers. Considering that we're using a single precision float variables, the amount of error is slightly large. The reason for that is we are only performing 5 CORDIC iterations. It does help with the reducing the computation time, but it has a slight negative impact on the accuracy. Now we have tested the correctness of the file. Let's press the HLS synthesis button. So this is the synthesis result of the CORDIC baseline implementation. The report tells us that the loop was automatically pipelined, which is good. But the problem is that the II is currently 15, which means that it takes 15 cycles per iteration. This definitely is not a good sign. To find out the reason, let's look at the guidance tab. The tab says that it was unable to enforce a carry dependence on current sign. So let's go back to the code to figure out what's going on. If we look at the code, current sign is updated every iteration, and the updated value is used at the next iteration. This means that the next iteration cannot proceed until the current sign computation is complete. But remember that we set current sign to a float type variable. Float addition typically takes around 10 cycles, so the next iteration cannot be pipelined to II equals to 1. Same problem exists with the variable data and factor. It has a dependency with the previous iteration. The second type of problem is that there are still some multiplications, multiplication of sigma. So the calculation of the loop carry dependence is getting even more complicated. Also, the factor is getting multiplied as well. So these two problems exist in multiple places. So we need to optimize this baseline design. What we're going to do is change the variable type to efficient fixed point representation so that the loop can be pipelined to II equals to 1. and we're going to learn the basics of the fixed point representation in the next class. Let's summarize what we learned today. CORDIC is an efficient method to calculate trigonometric functions without costly multiplication, and we implemented baseline CORDIC algorithm in C. But the synthesis result shows that the floating point implementation of CORDIC has poor performance with II over 10 cycles. So we're going to optimize the floating point implementation with fixed point representation in the next class. So see you then.